In this video, I'm going to write down an explicit proof of Theorem 3.11, which we stated in our last class before the break. I'll also give an example of a metric space that isn't complete. So, before I state this theorem, and before you go on, you should first review your notes from the last class that we had before the break. In particular, you should review the definition of a complete metric space, proposition 3.f, and theorem 3.6. Recall that a complete metric space is a metric space in which every Cauchy sequence converges. Proposition 3.f, it said that any Cauchy sequence, first of all, is bounded. And part B of proposition 3.f said that if you have a Cauchy sequence and it has a subsequence that converges to a point x, then in fact the full sequence also converges to x. And the last thing to review is, as I said, theorem 3.6. And what that said was that if K is a compact subset of a metric space and x sub n is a sequence in that compact metric space, then the sequence necessarily has a subsequence that converges to a point in K. And part B of theorem 3.6 said that any bounded sequence in Rk necessarily has a convergent subsequence. All right, so sequences in compact spaces have convergent subsequences, and sequences in Rk have convergent subsequences. Okay, so this is theorem 3.1, and the reason I'm giving you this proof via a video is that I essentially did prove it in the last class. I stated the proof. The proof follows from these results I just mentioned very easily. And also, I'm giving this proof because it's sort of an awkward place to start our first class after the break. Okay, so what did it say? So part B prime, it says that if K is a compact subset of a metric space X, then every Cauchy sequence in K converges to a point in K. All right. Part B says that compact metric spaces are complete, meaning that if you have a compact metric space, every Cauchy sequence converges. And part C says that Rk is complete. So Euclidean K-space is complete, meaning that any Cauchy sequence in Euclidean K-space converges. So these two statements, B and C, the statements that compact metric spaces are complete and the statement that Euclidean K-space is complete, are two of the most important theorems in this class. Okay, so first, the proof of part B prime. So we're trying to show that if K, or subset of X, is compact, every Cauchy sequence in K converges to a point in K. So for this, let's take X sub n then to be a Cauchy sequence in K. Well, because K is compact, theorem 3.6a says that our sequence necessarily has a convergent subsequence. And in fact, it has a convergent subsequence converging to a point in K. So, by theorem 3.6a, X sub n has a subsequence X sub n sub k converging to a point X in K. But now, we know that if you have a Cauchy sequence with a convergent subsequence, then in fact the sequence itself necessarily converges, and it converges to the point that the subsequence converges to. So, by proposition 3.f, because x sub n is Cauchy, and x sub n has a subsequence converging to x sub n itself necessarily converges to x, and that completes the proof of B prime. Now, part B follows immediately from B prime, because what does B say? B says that compact metric spaces are complete. So to show that, we would need to show that if X itself is a compact metric space, every Cauchy sequence in X converges. Well, take X sub n to be a Cauchy sequence in a compact metric space. Well, then because X itself is compact, this Cauchy sequence in X necessarily is going to converge to a point in X by part B prime. Well, that's what it means to say that our metric space is complete. Cauchy sequences converge. So, part B follows from B prime, so all we have to do is write. I'm going to write it here. B, this follows from B prime. Okay. Finally, we want to prove that Euclidean K-space Rk is complete. In other words, we need to show that if you have any Cauchy sequence in Rk, then it converges. Well, to do that, we'll start with x sub n, a Cauchy sequence in Rk. Well, if it's a Cauchy sequence in Rk, then by proposition 3.fa, we know that x sub n is bounded. So I've written if x sub n is a Cauchy sequence in Rk, then it is bounded by proposition 3.fa. But we know that any bounded sequence, or set in general, is going to be contained in a compact K-cell. That's proposition 2.k. So I've written, therefore, x sub n is contained in a compact K-cell by proposition 2.k. Well, now what do we have? We have that x sub n is a Cauchy sequence contained in a compact set. Well, part B prime then tells us that x sub n is convergent. Remember, B prime said that if you have any Cauchy sequence in a compact set, it necessarily is convergent. So, in particular, our Cauchy sequence here, which was contained in a compact K-cell, necessarily converges. Okay, so that proves that Rk is complete. So, I'd like to now note that it's actually easy to produce metric spaces that aren't complete. In other words, it's easy to produce metric spaces in which Cauchy sequences don't necessarily converge. And this theorem here tells you how. What does it say? It says that if you start with x, any complete metric space, so for example, from the last theorem, x could be any compact metric space, or x could be Euclidean K-space Rk. Well, if you then take y to be any subset of x and you view it as a submetric space, then y is going to be complete as a submetric space of x if and only if y is actually a closed subset of x. Alright, so the complete submetric spaces of a complete metric space are precisely the closed subsets of x. Well, in fact, this is on your most recent assignment, assignment 4. I think it is question 4 of the type B problems. So, what does this mean? Well, as a specific example then, we can say that y equal to, say, the open interval 0 infinity, when viewed as a subspace of R, is not complete. Is not complete, then, when viewed as a submetric space of the real line. Well, we know that R is complete, but because Y is not a closed subspace of R, Y is not going to be complete, provided we believe this theorem. If you wanted to prove this directly, it's not very hard. How would you do that? Well, if you wanted to do that, you would want to exhibit an example of a Cauchy sequence in here which doesn't converge to any point in the submetric space. So let's see if we can do that. So for example, we could let x of n be the sequence 1 over n. Well, then, what do we know? Well, we know that the limit of 1 over n is equal to 0 in the full metric space R. So, because we know that convergent sequences are always Cauchy, we can say that 1 over n is a Cauchy sequence in R. So, our sequence 1 over n is a Cauchy sequence in R. And that is theorem, let me just check, 3.11a. So theorem 3.11a said that Cauchy sequences, that convergent sequences rather, are Cauchy. So theorem 3.11a. Now, it follows, in fact, very easily, and you can check this, that 1 over n is also a Cauchy sequence in Y. The submetric space Y. And that's just because the submetric is just the restriction of the full metric to Y. Okay, so now we have an example of a Cauchy sequence in Y, and we want to show that it doesn't converge to a point in Y. So we can suppose that the limit of 1 over n is equal to y in Y. Well, then it's down. It's easy for you to check that the limit of 1 over n would also equal to y in R. And you should check this using epsilons. You should also check that statement up here that said that 1 over n is also a Cauchy sequence in Y. Okay, But we know that our sequence 1 over n is also converging to 0 in R. So if it converges to 0 in R, and it converges to y in R, it must be true that y is equal to 0 by the uniqueness of limits of sequences. So, hence, we must have that 0 is the same as y. And remember, because y is supposed to be in the set y, there it is up here, that means 0 is equal to y, which is in y. But y is supposed to be this open interval 0 infinity, and that is a contradiction. By the way, that statement that limits of sequences are unique, if you want to check your note, is Theorem 3.2, Part B. So let me just write that in here. This is Theorem 3.2b. Okay, so because we have this contradiction, what are we contradicting? We're contradicting the possibility that our sequence 1 over n converges to a point in y, so it must be true that 1 over n doesn't converge in y. So finally, therefore, the limit of 1 over n does not exist in y. So what have we done? We've produced a Cauchy sequence in y that has no limit in y. That means that y is not complete. So therefore, y, the submetric space of R, is not complete. And in fact, the proof of the general theorem that's on your assignment, which is to say the proof of this theorem right here that says that the complete subspaces of complete metric spaces are precisely the closed ones, is very similar.